Yeah, welcome. Today we start with section 2, and I hope that I can do much of section 2 this week. And then next week there will be section 3 about module categories. I have to decided to say essentially nothing about higher categories. That's just not enough time, and then use the last week for applications. There is one small part from section 1. I have in addition. You had the question concerning your Van-Helder theorem. We introduced this in the context of the building categories, and according to details that we find on NLA, the Van-Helder theorem is not surprisingly valid somewhat beyond. They give the precise conditions there, namely. It holds in what they call a homological category. And homological consists of 3 parts. One is easy. You have a zero object. The second is a property called regular for category, which is morally that there is a good notion of image factorization. But the details are there. And then the third is admitting an intrinsic notion of what called the normal subobject, in other words, the normal subgroups. And this is called a proto-modular category. Both of these properties here cannot be explained in just two lines. So we come to section 2, which is monoidal categories. For the first part, the level of sophistication is considerably lower than what we did last week. So in particular, we try to be a bit quicker, but still I will need some time to not just give definitions, but also motivate things. And I start with section 2.1, which I call tensor product. Recall my motivating example. This was what we later on called oriented cobordisms in one dimension. And we had objects which are disjoint unions of oriented points. And morphisms are arrows between such configurations. And one possibility would be an arrow here from plus to plus. And maybe one from, if we take this plus to minus. And then you could take a different one. You take this one and take, just to remind you of the conventions, minus, minus, and say, well, from minus to plus here. So these are two, but they consist of direct sums, so it's natural to admit direct sums of such configurations. So you could just say a direct sum here is, it's a direct sum. I do not even draw it. You just put this configuration below this one, and then it's again a configuration and a null configuration. And this gives a functor. Call this category C, from C, 2 copies of C to C. And well, actually, it's almost trivial that this is a functor, but it's a nice exercise to check that it's indeed true. This would be 2, 1. To 2, just a short remark, which will be relevant to generalize this. The direct sum that we are using here, disconnected sum, is associative. But I have to add something, and it has the empty set regarded as an empty collection of oriented points as a unit with respect to a direct sum. And you should remember from, or look up from 157 that the direct sum is really the co-product in set. When we talk about sets, and here we have sets of points, so that is relevant here. And thus, strictly speaking, we have, if you look at, say, objects, let's call them x and y, z, the direct sum of x and y, and then the direct sum with z, and the direct sum of x with the direct sum of point z are not equal. They are both, since this is a co-product, it's defined by a universal property. So they are both defined by universal properties, but by different ones. Here it's a one where you first, different combinations of universal properties. But on the other hand, you know, since this is universal, it determines the object up to unique isomorphism, and therefore they are isomorphic canonically. And they have a canonical isomorphism consisting of compositions of canonical isomorphisms. And in this sense, you can say that this is associative. But depending on what you want to do with it, you might have to account for those isomorphisms. So strictly speaking, you would say this is not associative on the lowest, but associative on the upper isomorphism. There are situations where these are important. And a similar structure, similar structures you have for the categorical vector spaces. Then you have a tensor product over the underlying field, and you have the field itself as a unit. And I will say a little bit more about associativity, not on the nose afterwards, but in any before that, let me just define, motivated by these two examples, what one wants to call a tensor product. Not yet. We need some more details for that. So we define the notion of a tensor product. So C is a category. And then we say tensor product on C is a functor, which we denote by this tensor product simple from C cross C to C. And that's it. If you just say tensor product. So in more detail, whenever we have two objects in C, then we can associate to them an object which we call X tensor Y. And if you have two morphisms, then we can have a tensor product of morphisms. And of course, there must be, this goes from, if this goes from X to X prime, and this goes from Y to y prime, then this one goes from x tensor y to x prime tensor y prime. Now, if you write down what it means that this is a functor, then you have two requirements: one, compatibility with identities, meaning that the identity on the object x tensor y is the tensor product of the morphism identity on x and identity on y, and compatible with composition, which says that for any four morphisms which are pairwise composable, one has f prime tensor g prime composed with f tensor g is the same as f prime composed with f, so those have to be composable tensor with g prime tensor g, and this is sometimes called the interchange law.
That's composable tensor g prime g.
Good, good. I think I said composed, and thank you. But then, in order that we use this tensor product really for a given category, we want to have it compatible not only in this way with the structure of the category, but also with the principle that I use several times, that in a category it's not so sensible to say that two objects are equal, but only equal up to isomorphism. And that is precisely what we should have or could have also said here. So let's, before formulating the definition of monoidal category, let me give an example. This is vector spaces. Again, so we have two functors obtained from, say, C cross C, or C to C, which are obtained by composing the tensor product either with the identity. That have to do it. Yeah, it doesn't matter. So the identity functor and tensor product, or the other way around. So if we apply this to a triple of objects, here the first tensor, the second and third, and then the first one with the result, and the other one the other way around. Now this tensor product here, well, is really what I call tensor product over K, which generally which we have defined also in the context of rings, tensor product over ring. And remember, and this was example 187, this is defined via a co-equalizer. And the co-equalizer is a particular co-limit, which is defined via a universal property. So it's not unique, but unique up to unique. This is individually now here and here, but if you do it in two different, if you compose it in two different ways, then we are using two different combinations of universal properties, and therefore, just like I said here, there is there is the two objects I get when I apply this to a triple of objects in C is they are isomorphic and even canonically isomorphic, but they are not equal. And we should better keep track on them. Now, in the case of vector spaces, we could avoid this, and in fact, in we say typical beginners linear algebra classes, one simplifies the tensor product associative, and when one applies these things really is using is that both of these combinations are maybe I write it out. So both the linear maps, I just write term K for the linear map, so for the morphism in vector K from say U tensor, and this is tensor over K, V tensor W to any X for all U, V, W, X, and C, and the other, the linear maps from the other combination, U tensored with V tensor V to X, in canonical bijection. With, well, how did we define this? By a co-equalizer, but you can formulate it differently. That is, say that you start with the Cartesian product, where you have bilinear maps, and you have a universal property which relates this to linear maps from the tensor product. And so here we have three factors. So here we can say both of them are in canonical bijection with three linear maps from the Cartesian product of the vector spaces to X. And then if we use them, because they are also canonical, we combine them, so we get a canonical isomorphism, canonical linear isomorphism between these vector spaces, and then using the Yoneda lemma, we can write this as a canonical. Right, this implies a canonical isomorphism between the objects, and so altogether what we see is that for any triple U, V, W in vector spaces here, these two vector spaces are canonically isomorphic. And now that we include in our definition, and we also give it a name. So that would be 2,6. So, and we call this the monoidal category. Sometimes, in particular in the older literature, this is also called a tensor category, but this is nowadays used for something with additional structures, so I will not use that term. So what is this? This is a sextuple of things. C tensor 1 A U R, where C is a category. The tensor here is as defined here, a tensor product on C. One is a unit for the tensor product, and A and UL, UR are natural isomorphisms. Right, A is a natural isomorphism between those two functors here with components which we then call alpha u v w, for every bit of objects going from u tensor v tensor w to u tensor v tensor w, and ul and ur are natural isomorphisms. I haven't written the functors, so let me give them names. So ul would go from the identity of C and then tensoring with unit to the identity of C, and ur corresponding with starting with the identity of C. And this is kind of symbolic notation, but I think it's clear what you mean by that. So this has analogous components. Say ul v, which goes from v tensor 1 to v for all v in C, and analogously urv. And now these are the data that you have, and these have to satisfy various conditions, which can be summarized as the commutativity of three diagrams. This is continued such that the following diagrams commute. There's a diagram called pentagon identity. This pentagon. And you take, there are several possibilities to write it. One possibility is you take 4 objects u, v, w, and x. Get your tensor by starting on the left, and you compare this to the same when you start tensoring on the right. And then between these two objects, there are two paths, two compositions of morphisms which only use identities. And I should have mentioned here that this not alpha. If I write something wrong, please. Of course, some people call it alpha. A here. This we call the associativity constraint, or somewhat shorter associator. And these are called unit or unitarity constraints, and I will call them just uniters, left and right uniters. And well, one possibility is that you first apply A to this tensor product here. You will then get to U tensor V tensored with W tensor X. And here we would have A, the component for U tensor V, comma W, comma X. And then we have a morphism here, which is A with components U, V, and W tensor X. And another possibility is to first use associativity inside, but then you get to U tensor, V tensor W tensor X, and you have here the identity on X together with an A. And I will not write the other morphisms because you can easily reproduce them. And from here by now using the associator on the second tensor product, you get to U tensor and then V tensor W tensor X. And from here to here, you let me see. Yes, you use associator in the bracket. And pentagon, and then you have two triangles, which involves besides the associator the unitas, namely if you consider tensoring with one, then tensoring, say, from the right, and then with something else, then of course via A, V, 1 and W, you get to V tensor A tensor W. But if you take here the UR V component tensored with the identity on W, you get to V tensor W. And why did I say 3? Because I have 3 natural transformations. So there is one triangle which involves both the UR and the UL identity on V, tensored with the left uniter for W. And the second part of the definition here, we say we have a strict monoidal category if A, UL, and UR, all components are identity morphisms. And there are two reasons for looking at this particular case. First of all, there are some interesting monoidal categories which are strict, but then more importantly, as we will see later, we can relate every monoidal category to a strict one. And very precise. Well, actually, this will take a bit of time. So we'll probably not go into details today. So one also, I call the unit here, sometimes it's called monoidal unit or tensor unit or unit object. All of this is in use. Just as I said, the pentagon describes the equality, so the commuting diagram, and here, equality between the composition of these two morphisms with the composition of these three, but all of them are isomorphisms by definition. So we could formulate this also as equality of the two composite morphisms that we naturally get by starting at any point in this pentagon and ending with any other point. And I mentioned this because later on in the course, I will also deal with similar diagrams which do not only involve isomorphism. And analogously, of course, for the triangle. As a further remark, well, it should be clear from the definition, A is structure. And in principle, also UL and UR, but they are you see, they are much simpler. So usually, well, in almost all situations, we can just take them as identities. do not anything wrong. So it's structure, and we impose a property on it by the pentagon. And in particular, there are it can happen that the given category C can admit or admits various different meaning that the corresponding functors you get are not naturally isomorphic tensor products. And I will give you an example, but not right away. I just mention first one important result. You could ask, well, what happens if I do not take the tensor product of multiple tensor products of 4 objects, but of more of them? And this is answered by Plane's coherence theorem, which says that if C is monoidal in the sense of the definition, then any two morphisms F and G between two given objects V, which are combinations of associators, uniters, and identities, and also their inverses, their isomorphisms, are in fact equal. So if I take anything more complicated, I can use the pentagon several ways, in several times, and triangle if needed, in order to show that the corresponding complicated diagram that I might start with actually automatically completes. No requirement for that. And let me just mention that in MacLean's book, this is in chapter 7.2, and also that you can look this up, for example, in section 3 of a paper by Wilson and 2 other collaborators, which I will add in the reference list. And I haven't done it yet, but I will do tomorrow. So in particular, well, this is more general than just any two bracket links of an arbitrary number of objects, so that's the special case. So we have already seen, now if we ask about examples of monoidal categories, with what I said before, vector spaces give a monoidal but not strict monoidal category, and also cobordisms, where we have done for the one-dimensional case, but actually this is true also for the let me see, what was my convention? It should have been 1, 1, 0, and then here d minus 1, where for any d here we have as tensor product, the disjoint union and the empty set as a unit object. Then an example for a strict monoidal category. Let's see, be a small category. Then you can look at the category end of C, where the objects are endofunctors and the morphisms are natural transformations. We have talked about this in the general case that we have functors from C to some C prime, but now we take C prime equal to C, and then we have a tensor product, which is this composition of functors. On objects and composition of natural transformations on morphisms, and this is well, composition is associative on the maps. And as a final example, well, two final example set, we can take as a tensor product the disjoint union, and then the unit is the empty set. But we can also instead, as tensor product, take the Cartesian product. And then the tensor unit is the one element set. More examples. At G be a group. We have already looked at the category of G-grade vector spaces, where the objects are G-grade vector spaces and the morphisms are grade preserving linear maps. And then this admits the monoidal structure, where we give the tensor product over K of V and W as vector spaces, the grading according to writing this as sum over all group elements. And then the G graded part, so V is G graded, so with components G and analogously for W. And then we have here the sum over all H, and then VH tensored with WH inverse G. And with associativity constraint the same as for vector spaces. And also, what is the unit? Well, it's the underlying field in grade E unit element. So one would have a decomposition here where 1G is K delta G. Now, this generalizes to the following, and this is an important class of categories. Where some we take the same category and the same tensor product, but different associator, namely A omega as follows. let me write it as follows: A omega G1, G2, G3. Where this stands, where there should be objects here, I take as objects those one-dimensional vector spaces which are in grade G1 and so on. And if I have it on the one-dimensional spaces, I can define it. Well, this already defines it on all graded vector spaces. So this is an has to be an isomorphism from this tensor product to this tensor product. And what we do is we choose in each of these a basis, call it UG1, and then analogously for the others, and we map this to some number depending on G1, G2, G3 times the other tensoring of the basis elements. So all right, basis here. To remind us where the omega here is. Well, this is a vector in this space, so I can multiply it by a number. So this has to be a number. Omega is a function from 3 copies of G to K. Well, to invertible elements in K. Now, if this is an arbitrary such function, it will not give me an associator, because the associator has to satisfy the pentagon condition. If you write down the pentagon condition for that, we get that omega of G2, G3, G4 times omega inverse. I have 5 terms, 3 on the left, 2 on the right, but I bring all to the left by taking inverses of 2 of them. And then I have G1, G2, G3, G4 times omega of G1, G2, G3, G4, omega inverse of G1, G2, G3, G4 times omega of G1, G2, C3. This has to be 1, and this simply means that this is not just a 3 cochain on G, but it's a 3 cocycle. So the omega it's 1 written multiplicatively. And also, and we use as a notation what I already have done here. If you take 2 different cocycles which are cohomologous, then they give the same monoidal category up to monoidal equivalence, which we have not yet defined, but we mention what that is. And yeah, that's it for this example. And the final example that I want to mention, and then we should have the break, is that A be a K algebra. And we have the category of A modules. Let me see, I have, no, of A bimodules. We call it like that. So objects are A bimodules, morphisms bimodule morphisms. And now what is the tensor product? We can take the tensor product over A as of bimodules as we have defined in example 187. So as a co-equalizer, as I mentioned before, and what is the tensor unit in this case? This is the regular A bimodule, so A regarded as a left and right module over itself, meaning that the left and right actions of A are just given by the product multiplication. And yeah, it's time to stop. And then I will continue with a few more comments, and then I go over to graphical calculus. Yes, for those on Zoom, sorry that we are slightly late. There have been some questions here from the audience. Let me continue, as I said, with some remarks. 14 is the following. Assume that C is K-linear monoidal. I have not really defined that. So this means it's K-linear and monoidal, but also the two structures should be compatible. So and it's easy to say how, but I don't want to write this out. And one is linear simple. Remember, meaning that the endomorphisms of one are just isomorphic to the ground field. Then it follows that all morphism sets, well, they are vector spaces in this case, but they are not just vector spaces, but they are free modules over the endomorphisms of one, over the K algebra K. Maybe I write home C to make this clear. And to 15, a remark. Which we will not need in the rest of the lectures, but I will explain why I nevertheless make it. There is no monoidal structure on the category which is called Hill. Maybe I write explicitly infinite dimensional. What is that? Infinite dimensional Hilbert spaces. So objects are Hilbert spaces, and morphisms are continuous linear maps. And I mention this because sometimes in the literature, or you see the opposite, or you think you see the opposite. If you look very carefully, then it might not be true. So I have written no monoidal structure. There is, I can define a tensor product of Hilbert spaces that's used all the time. So what would we try? Well, of course, we could try tensor product of vector spaces, and then define an inner product on the tensor product on that tensor product. So we would say, well, I'm using this physics notation for inner product, and that if we have two vector spaces V and capital V, capital W, and then if we have vectors of particular form V tensor W and V tensor prime W, V prime tensor W in prime, and then we could say we just take the product of the inner product in V prime the inner product in V and the inner product in W. That we can do, and it turns out this endows the algebraic tensor product. V tensor W with an inner product. So algebraic tensor product means that we define this by taking by having a basis of the form of this form and consisting of vectors of this form and allowing for finite linear combinations of them. And then this is let me call it right. And then take the Hilbert space completion of this completion with respect to this inner product. And indeed, we then get something which behaves like a tensor product. But remember the tensor product of vector spaces, we can we can do it via co-equalizer, but it amounts to saying that the tensor product has a universal property with respect to bilinear as opposed to linear maps. And the tensor product that we get this way, and we show not to have that universal property. Let me just write not universal. And for this, I should give you a reference. There's a paper by Garrett, maybe not paper, this could be a website, I think, and another one by Lim. And I will link them. And the link is here, it's example 418. And then another remark. It's a rather natural question to ask: if I have such a tensor product, is it exact for a given category, or maybe just left or right exact? And you can ask the same thing for the home pointer, and there's a general, rather general answer to that. And that I want to take up a bit. And we start with the situation that we have rings R and S, and we consider the categories of the right modules, which we call mod R and mod S. And then we have already seen that the tensor product over R with a given bimodule R as bimodule, this gives a functor. Well, tensoring, maybe I should write. So taking any right R module, I tensor with this given X, and I get something which is the right S module. And so any right module XR is mapped to XR tensored over R. Oh, this is U, maybe. S. And also taking the hom, let's call this this functor T for tensor, and the hom functor of S gives a functor in the opposite direction. Let's call it H from S right modules to R right modules, which takes any S module, call it a Z, and maps it to the morphisms with respect to S of XRS regarded as a S right module to Z. Maybe I also said S. And you can see this this has a natural structure of R right module, and one can show that these two functors are actually related, namely T is a left adjoint to H. So we have natural isomorphisms between morphisms in S, U tensor over Rx. I leave out the labels and any Z, and morphisms in R between U and S. And if we look at what I have said in 1.224, oh, by the way, I forgot to say this for those on Zoom. In the last 20 minutes or so last time, I switched the numbering from 1 to 2 for the section number, and from 200s to 300s for the rest. So that was just happened. It was so this is in section 1, where we have seen this relation that if T has a right adjoint, then it's right exact, and H has a left adjoint, and therefore it's left exact. Right, all these particular categories, but also in much more generality, and this is also called a tensor hom adjunction. For this particular case, and let me just write analogously in more generality. So in under mild conditions, which I do not want to specify, when we have a monoidal category, then the tensor product is right exact, but not necessarily left exact, and the hom functor is left exact, but not right. Of course, there are many special classes, categories, they semi-simple, where they are exact, but in general they are not. Wait. No, semi-simple is not. So now that's the general setup. Now for some time, I will talk about graphical string calculus, which we have done before, but now we extend this, and only now it becomes really interesting. Maybe string calculus 2 here. If C is strict monoidal, strict is important here, not as important as it might seem in the first at first glance, and then it admits a graphical calculus. We'll just call it string calculus, which I have to specify. If C is not strict, then this is not directly true, but still equalities between morphisms can be treated. Let me just put it like that, and I will say this in more detail once I have the relevant pictures, or you could develop a more general calculus, which actually has been done. Unfortunately, I haven't written down the reference here, so it's not something you typically would want to do, but for some applications, people have done it in particular applications. So the point here is that strictness is something we will use in the description of individual graphical representation of individual morphisms. But if we have two pictures for two different morphisms and say the morphisms are equal, then this holds in the first place for the strict case, but there is a unique unambiguous way to insert associators at appropriate places in order so as to represent by the equality between the pictures, also an equality between morphisms in a non-strict category. So how do we do that? Remember from categories, what we had was that we use a line. This straight line, but it doesn't matter. That is straight to depict an object X, or also the identity on X. And the morphism between X and Y would be distinguished, associated with a distinguished point here, say F. But we in order to make pictures easier to recognize, we have put this in a little box or coupon. And drawn it like that. And then we have talked also how associativity of composition is realized in terms of these pictures. And one important aspect is what is relevant is only the linear order of morphisms along lines. So this is really a one-dimensional graphical calculus. In a monoidal category, we cannot only compose morphisms, we can also tensor morphisms. Therefore, we have a second dimension. And so we get in a monoidal category, we have a two-dimensional string calculus. And I maybe take some more space for that. So what we do is we think of such a morphism not as something along a line, but embedded, say, in the plane, or more generally in something I would call a canvas. On a canvas. And the relevant canvas is the generality that we have here is something two-dimensional, which is technically one can say it comes with a two-framing. For us, this simply means that we have a notion of first distinguishing the lower and upper boundaries here of this canvas from the left and right. So we have a two different directions really. And then also if we would compose some arrows along this curve here by some kind of parallel transport, and we have a distinguish. It fits with the distinction between in and out, as it should for F, but also we know we are allowed to change this a little bit, and we will get the same morphism. Maybe we fix also the endpoint here for simplicity, but we are not allowed. So we want to have progressive graphs in the sense that we always have a non-zero component upwards in our lines. And you can formalize this, but I think it's pretty clear what now analogously, is when we consider composition, G after F, assume they are composable, is the same. The morphism G after F is related to this. Well, these two pictures are related by a local move, and then we can use this for understanding associativity in graphical terms. We now have something, so this goes in one direction, we have something in the opposite direction. When I draw this now, in principle, I should draw the canvas, but I will omit this always. And it will always be the same canvas, at least for a long time. We now also have that if we take two morphisms, G1 and G2, this form, then by a local move, we can replace it by G1 tensor G2. In a single coupon. And now notice if we use the same argument as for associativity here, we get associativity of the tensor product on the nose. So therefore, this directly applies to strict monoid and not general ones. Also, the unit we take to be strict. And then we can look at the situation that we have some morphism from X to Y and tensor it with the identity on the unit element. But one tensor X is not only isomorphic to X, but equal to X. And analogously here, and what you see is, therefore I draw this as a line in this form in the first place. This is the same as just drawing F, and here we would have one tensor X, but this is the same as X. And here we have Y, and then you see that the tensor unit in this graphical calculus is, we can call it invisible. We can put it anywhere. but do not see it, or sometimes people also say transparent. And then remember this this comment here. We sind if we are just in the situation of categories, this doesn't matter anyhow, but this will still be true now. We can also, in this situation, move the G1 a bit up, G2 a bit down. And draw this instead in this way, and this is the same thing. Actually, what you could say is, well, one way to think of this is that you have you have here composition with the identity morphism from below, and here composition with identity from above. Whereas here you have compositions with identity morphisms here, and then this is nothing but the interchange law for the particular case that identities are involved. And of course, you can also draw the general thing with arbitrary morphisms, and then only the labeling should be more careful. And as I said, I will not precisely formulate what you are allowed to do and what not. It's morally what I said. And if you want to know details, then there is the original paper by Floyer and Street, which is very readable, and there is a review by Salinger, and there are various other ones. Only refer to them. So, and the finding of mine, this part is the following. When I draw this canvas here, I have quickly removed it again, but it's really always there. So let me draw it, for example, here again. And then you could say, well, it's somewhat unnatural that we label, well, here we have object labels, here we have morphism labels. So we think of this as a stratified manifold. We have one-dimensional strata labeled by objects, zero-dimensional ones labeled by morphisms, and we have the two-dimensional ones and they are not labeled. And it would be more natural somehow to label also them. If we do that, actually, well, there is actually a situation where this is precisely what one is doing, and this is a graphic calculus for two categories. And it turns out that a monoidal category, which I have defined, is the same thing as a two category, which I have not defined with one object. A two category, just like category has two layers, object and morphisms, and two category has three layers, objects, one morphism, and morphisms, and contour morphisms. And we would then label the two strata here by objects, the one strata by one morphisms, and the zero strata by zero morphisms. And because there is only one object, a single object, we have the same label everywhere here, and therefore we don't have to write anything. To make this precise, when I say it's the same as, then really there is a notion of the de-looping of a category, and the monoidal category is really the de-looping of a monoidal category is the two category with one object. This is already all about section 2. This was graphical calculus. Section 2.3 is still more graphical calculus. But for a particular case, for algebras and co-algebras. And you all know the standard definition of, maybe I have even given it, of a unit of associative K-algebra and similarly of a co-algebra. If you should actually not know it, then there's no problem, because we'll get it as a special case of the definition I now give. Yeah, why not? I start with the actual definition, but very short. So by algebra, I mean unit associative algebra. As a K algebra, I write this instead in the category vector K for now, and then I generalize this afterwards. So what is this? This is a triple A mu eta, where A is a vector space. So this is an object in vector K. Let me write it in this way. Mu is a K linear map. From A tensor A to A. Well, in the usual definition, one would rather say a bilinear map from the Kronecker product of A with itself to A, but now we use the universal property of the tensor product over K. And that we call the multiplication of product. And eta, well, the usual definition is that there's an element which is a unit for the this multiplication, but we can reformulate it by saying it's a K-linear map from the field to A, and which map? It's the one which sends the number 1 to let's call it E to the unit object in A. And this extended by linearity. These are subject to the requirement that mu is associative, which we can write as mu composed with mu tensor times identity is the same as mu composed with identity tensor mu. But this is associativity, and then we have unit properties, mu composed with eta tensor identity is the identity, and also mu composed with identity tensor eta. And then we have the definition of a co-algebra in vect. This is a triple, it's from one call it C. C delta epsilon, where C is again a vector space. Delta is now a linear map. I don't write this all the time in the opposite direction from A to A tensor over Ka, and epsilon is a map here in the other direction, such that analogous, sorry, I decided to call this C, such that I get a similar requirements as here, namely co-associativity, saying that delta tensor with the identity on C composed with delta is the same as identity with the tensor delta composed with delta, and epsilon tensor identity with C after delta is the same as the identity. This is the same as identity epsilon. And concerning notation, it is common to just abbreviate this triple here by the vector space A and then here C. In some cases, it makes sense to distinguish between the algebra and the underlying vector space. In that case, I will put a dot on this and analogously for co-algebras. And more generally, whenever I have an object together with some additional structure morphism, then one uses for the tuple of that the same label, the same name as for the object itself. But if it's important, then I will put the dot on the underlying object. And just remark that I don't write down, just like in the situation here where I relate morphisms to objects. So this would be a particular morphism corresponding to a particular object. More generally, whenever I have a monoidal category and one has morphisms from the identity, the unit object, which in vector spaces is the field K, to some other object, sometimes one calls and also thinks of this as elements of that object. I will not really use this, but you will find this terminology in the literature, so that's good to know. Now, the point with formulating the definition in this way is that once you have this definition, you can easily generalize this to the notion of an algebra or a co-algebra in an arbitrary monoidal category. C. Then the tensor product is what it is, and there is, well, we could in that sense, as I just mentioned, talk about elements, but I will not do it. Instead of the field K here, I already have written it here. There should be a K here. Now there will be a 1, and everything else remains like this, except that, well, not everything else. Instead of K linear map, which is a morphism in vector spaces, we have to say morphism in the category in C. So now I've done it for everything, yes.
Should be
in category in.
You wrote
Here, thank you. So to be precise, well, are there any complaints? Further complaints? I have to refine this. This is the definition as you usually see it, and as you also will see it if you look at typically papers where I use the notion, but this would be the definition that we have in a strict monoidal category. Why? Because what is this here? This mu is a morphism from A tensor A to A. So here we have such a morphism. We tensor it with the identity, and then take the object here and multiply. So on this side here, we have a morphism from this object to A, whereas on the other side, we have a morphism from A tensor A to A. And they are not equal, but only isomorphic if the category is not strict. So we really should write in a non-strict category. Instead, we have mu composed with mu tensor identity on A is not the same as mu composed with identity on A tensor mu, but we first have to we have to get the domain right, and we can do this by composing this with A. And analogously for the unit, we have mu composed with eta tensor identity. This is not a morphism from A to A, but it becomes a morphism from A to A if you compose this with the inverse of the left unit for A. And then we can write this is the identity, and analogously this is the same as mu composed with identity on A, tensor eta composed with right unita inverse. And analogously, in the case of co-algebras, we would have delta tensor identity on C composed with delta cannot be the same as identity on C composed with delta, and then tensor delta composed with delta. Now we have to we have three copies of A in the codomain, and therefore we have to put an A, an associator here, well, or the inverse associator here, and you can imagine correction for the co-unit properties. I will call, I should have maybe stressed this already. I will just call these structures algebra and co-algebra. Some people like to refer to reserve this this terminology for vector spaces, and then they call this an algebra object, or also a monoid object, not just the monoid. I will typically say algebra and equal. And what is nice is maybe a time for the break. Remark. And you will get various realizations of that is that various statements about co-algebras or algebras in vector spaces directly generalize by precisely doing what I did here, replacing linear map by morphism and so on. And the easiest way to see this in many situations is to use a graphical calculus, which we will do after the break. Let me just mention one thing. The unit or co-unit, if it exists, is unique and the argument is one. But also that is nicely done graphically. Okay, then we have some step. It's an identity. So if this G1 is from X1 to Y1, I could say I insert here the identity on X1. And so this I write G1 equals G1 composed with identity on X1. And instead of a coupon, I just count it like that. Because if I do that, then this picture being equal to that picture is let me see. I have I have not been precise here. Let me see. I should I should do it again. I didn't have this in my notes. G2, and then we say that we in this way have done. But this really stands for well, one way to say it is G1 composed with identity on X1, tensored with identity on X2, composed with G2, yeah, and then we use the interchange law to say this is the same as G1 after identity on X2. No, wait. G1, that's nonsense. A G1 composed with this, tensor this, that's the same as a G1 tensored with the identity on X2 composed with identity on X1 tensored with G2. And what is that? Well, this is precisely what we let me see. This is as a picture G1 in the identity. And then I have the identity. Yes, correct. It should be like that. And I have put brackets here, and here I put brackets like that. Where I say here I compose, and here I have composed first and then tensor. And here I first tensor and then compose. And it was not correct to this point should be here.
Thank you.
Just a small correction. When I draw, I quickly have drawn this picture concerning the interchange law, where I said I moved these things around. It was correct to say I add an identity here and identity here, but of course I have to do the same thing on the other side. And I have put this identity here, which of course I can still do, but that's not what gives me the interchange law. And to be more explicit here, what we do in this picture is we first compose here, and then take the tensor product. Whereas here we first take the tensor product here, and then compose. But in the graphical calculus, it is identically the same because these two pictures look different, But with respect, if we implement a correct interpretation by saying that it's an equivalence relation that we divide out, then they are really the same. Or we can say we identify via pictures which are related by a certain type of local moves, and we could make this explicit, but I will not. I will come to the graphical calculus for algebra and co-algebra, but I have to take a detour because I want to mention also a few examples. And before that, there was no time to do it. It's just another definition. Let's say we have a haploid, which is an unconventional word, maybe algebra or also co-algebra. This is an algebra or co-algebra with the property that the morphisms from 1 to A are just multiples of the unit, respectively the morphisms from A to 1 are just multiples of the co-unit. So in short, 1 is contained in A precisely in one way, and this in the other direction. Instead of haploid, we could also say connected. Connected is also, in particular, when we deal with Hopf algebras, used in another sense. Both of them are not ideal. I will not use it very often. Maybe I write every time then what the definition is. Now, examples. That's why I introduced this. In VecK, there is only one haploid algebra, namely K itself, because as a vector space, every object in vector space is a direct sum of dimension many copies of the field. And then that means that, and this is the tensor unit, so this follows directly. And in any monoidal category, the tensor unit, together with all the structure morphisms being identities, well, identity on one, where I identify this with identity on one tensor one. Remember, we are strict or pretend to be strict, is an algebra and co-algebra so either regarding this as a product or as a co-multiplication, and also it's haploid, of course. So that's not so interesting maybe, but it's an example. And then, since this is a side remark, but a long side remark, I have some sub-labelings here. I first introduced the following definition. An invertible object in C, when any statement I make only makes sense in monoidal categories, I don't say monoidal all the time. So C is a monoidal category, is an object, I will often call it L in C, such that there exists another object L prime in C, such that L tensor L prime is a morph is isomorphic to the tensor unit, and exists an L double prime such that L double prime tensor L is isomorphic to 1. Such objects have many special properties, and I mentioned a few of them. The first one actually does not really make sense yet for us because we haven't had the corresponding notion. So this is in the Ettinghoff et al. Book, proposition 2.11, and some statements after that. The first is an invertible object is in particular dualizable. For those who know what it is, they know, and otherwise we will take up this later on. And in fact, L prime, let me see. Well, no, I don't write it down. So L prime, and this doesn't should be double prime here. One of them corresponds to the left dual, and the other one to the right dual of L. And then actually it follows that L prime is isomorphic to L double prime. This is again the usual argument of showing that an inverse is unique. In this case, it's unique after isomorphism. And also if L1 and L2 are invertible, then the tensor product is invertible. Where you just identify what is the other corresponding prime or double prime objects, and that means that if we look at the subcategory consisting only of invertible objects, then this is in fact a monoidal category again. So it's a monoidal subcategory. But a full subcategory of invertible objects. Monoidal. The same tensor product inherited, and this is sometimes called the Picard groupoid. Of C, well, the name comes from also the notation L here. If I look at the category of vector bundles, then the invertible objects are the line bundles. Therefore, L and the category of line bundles. Picard. And sometimes one does not look at this groupoid, at just having the invertible objects, but completely with respect to direct sums, also direct sums objects, and which of them is denoted by this symbol might vary in the literature. But for us, more important is that this descends to the Grothendieck group of C. Remember, this is the vegan group of classes with respect to isomorphism of objects in the Abelian category where the addition comes from direct sum, and So we define for C abelian and monoidal. We define a product on the Grothendieck group. Which sends the Cartesian product of the classes of X, objects X and Y, to the class of the tensor product of X and Y. And from the fact that the tensor product is associative up to isomorphism, it follows that this is an associative multiplication. And also, it has the class of the tensor unit as a unit. So this endows the formulate this as a lemma. If I take a Grothendieck group together with this multiplication and the class of the unit element, then this is a unitary ring. And well, you have to, of course, check some aspects, but this is completely straightforward. Maybe I write for completeness. Associativity, just this is no. So if we take X or Y as Z, and this is by definition X tensor Y as Z, which is by definition the class of X tensor Y tensor Z, but this is by definition of the Grothendieck group the same as the class of X tensor Y tensor Z, and then you do the steps backwards. And analogously for the unit, and then something which we only have done actually implicitly is the following. We also have to check that X multiplied with the sum of Y and Z, where this is addition in the Grothendieck group. Well, this is by definition X times, and then here we have the direct sum of Y and Z. And now we use, and this is the same as the class of the tensor product of X tensor Y direct sum with Z. And what we didn't write out explicitly is that this is the same as X tensor Y direct sum with X tensor Z. And then this is again the sum of the class of X tensor Y and the class of X tensor Z by definition, and then one step more, and then you are like X star Y plus X times Z. So we have so a star distribute. So plus, and then also remember we had this choice of basis of the ring consisting of isomorphism classes of simple objects. In the semi-simple case, but we can also more generally say that if lambda was the capital lambda was the set of isomorphism classes of simple objects. So if we look at the product of two of such particular elements of the quadratic ring, by definition, this is the class of the tensor product of the corresponding representatives, which we have called y lambda, respectively y u, and this is then easily written as this stood for the occurrence or multiplicity of y nu in this tensor product. So in a composition series in general, nu, and in the semi-simple case it would just be a direct sum, and this number we will often call n lambda mu nu, and then we see that we have lambda star mu equals sum over nu in lambda, and well, we can write it in that way, where we this means just the n lambda mu fold sum of nu with itself, and this is often called the fusion rules. In particular, in the case that's the semi-simple of the category. And this is now relevant for us because if we restrict to invertible objects, that was our first detour, and then we got to the second quadratic group. Since it's a ring, we also call it the quadratic ring. And now in this ring, as a ring, we have a subgroup given, but with respect to star, given by the invertible objects. Because we have seen, because of this property here, which I erased, that the tensor product of two invertible objects is again invertible. This is sometimes called the Picard group. So the group in the quadratic ring of isomorphism classes of invertible objects. And maybe as a further remark, first of all, if C admits what is called dimension function, and I will give examples of that later on, then in general, this will be for a linear category. This will be a number in the ground field, and for an invertible object, this can only be plus or minus 1. And there is also what is called the Frobenius Perron dimension. I might not define this explicitly, so let me say it in words. Assume we are in a situation that there are only finitely many, that is set lambda is finite, or also slightly more general. Then, well, these n's are by definition non-negative integers for given lambda, say. For matrix, we can regard this as a square matrix n lambda, where the entries are non-negative integers, and then this by result of Frobenius and Perron, this has a unique eigenvector with respect to a largest real eigenvalue, and the corresponding number is called the Frobenius Perron dimension of L of P, and this is always +1. So if we take that, we also see when we do this, if we have a class of an invertible object and tensor this with any lambda, then this is again a class of a simple object and not a sum of such. So these n's are that I get are really permutation matrices. So now, how did we come to that? I want to say give examples of algebras, and the point is that I want to give examples of algebras which, as objects, are direct sums of invertible objects. So we consider an object in C in a monoidal category, A, which depends on some gamma, where gamma is a finite group, which as an object is just the direct sum over all elements of gamma Li, whereby Li I mean an invertible object. So all of these invertible. And also I assume that Li and Lj are isomorphic if and only if I is equal to j. And also you can see easily that Le has to be isomorphic to the tensor unit. And then it follows in this case that Li plus Li tensor Lj is just isomorphic to Li plus j, where this is addition in the abelian group gamma. And in addition, we now also assume that this is done very often in literature, stated somewhere and then not mentioned later on again and again, that one is linear simple. If we all, well, in this case, we have the following lemma. The Ender functor, just write functor, Tx from C to C, which is tensoring by X. So I send any object to Y to X tensor Y is an equivalence if and only if X is invertible. And the idea of proof is the following. By construction, if I take T for X tensor X prime, then this is the same as Tx composed with Tx prime. But now if you go in one direction, if you assume that X tensor X prime is isomorphic to 1, so X is an invertible object, therefore there is function X prime, then it follows that this T X tensor X prime is isomorphic to the identity functor on C, and that means in particular it's an autoequivalence, and because of this composition here, also Tx itself has to be an equivalence. And in the other direction, maybe I don't write that. If Tx isn't autoequivalence, then in particular the tensor unit can be written as Tx of something, and this should and from that you deduce then that X has to be invertible. And under condition, under this additional condition, you have to be calculated. Then this is just used as a one ingredient in obtaining obtaining the result, and then we formulate. We will also need the following, which I write as a remark. We will not. But it's easy to see actually that the associator of C restricts to an associator on this Picard subcategory, include direct sums, and in particular, then this gives a 3 co-cycle on the Picard group. So let's call this psi. And now assume that there is a 2 cochain, I call it omega, in gamma. In such that if I take the co-boundary, then I get the restriction of psi to gamma for gamma some subgroup of the Picard group. And select for every I and j in gamma a basis lambda ij in the morphism space one. This is one-dimensional. Li tensor Lj to Li plus j. And that Uij, I have to tell what, for the moment, it's just a definition, omega of ij, so a number times this element lambda ij. And mu as the sum over all I and j in gamma of something which I only write in diagrammatic notation, namely I take A, this is this object here, I take the restriction. We had this restriction and inclusion maps, which when suitably composed give us idempotencies into Li. And I do the same for J. And then I take here the morphism Uij. And what I get is Li plus j, and I embed this in A. So each of these is a morphism from A tensor A to A, and then the sum of those I call mu. And then you can check when the object A defined there, this morphism U from A tensor A to A here, and a unit which is simply which is the embedding of 1 into A, and by assumption here this is precisely that this is unique up to again a number, and the number is, well, there is some convention on that implicit here. Actually we typically we want this these two cochain to be normalized. If I or j is equal to 0, we simply take it this number to be 1 and not something else. And then this is an algebra. And see, this in itself is rather nice. We call this also the twisted, or omega, or more precisely psi and omega twisted group algebra. So what do we have here? We have, first of all, the subgroup, the Picard group. We have a 2 cochain satisfying this requirement, and then you just calculate that this is an associative multiplication. But not only that, the result due to Ostrich. Also, I will link this, the example to 1. Says that first of all, this category, including direct sums, pick C, is equivalent as a abelian category to the category of pick C graded vector spaces. And then every I didn't define that. Semi-simple. Oh, I did define semi-simple. So did I don't remember. I wanted to do it. So we call an algebra semi-simple if its category of modules is a semi-simple. Every semi-simple indecomposable. Indecomposable means we cannot write it directly. We cannot write it in a non-trivial way as a direct sum of algebras. Algebra in the Picard subcategory is of this form, meaning is of the form that we have such a subgroup gamma of Picard group, and we have such an omega satisfying this property. I'm still not finished with examples, but maybe I can take these examples next time so that I can present a bit more graphical calculus here. So back to string calculus. So far, all the coupons I had were either arbitrary morphisms, or labeled by arbitrary morphisms, or they were specifically identity morphisms, so we could leave them out. Now in algebra we have distinguished if there's an algebra, we have this distinguished morphism, multiplication and unit, and for these, we introduce separate notation. So mu is a morphism from A tensor A to A, and we define this picture here to stand for mu. And I should maybe write mu here and write A here and here, but it should be very often use this word one algebra, and then there is no need for the labels. And similarly, the unit, which is a morphism from 1 to A, we write in this form. And since the unit is invisible, we just write just in this form. And analogously for the co-unit, for the co-multiplication, delta of a co-algebra, we draw this in this way, and the co-unit, which goes from C to 1, we write as this form or just in this form. And then assuming we are in a strict category, we can use the graphical calculus to, well, here we don't have multiple tensor products, so we can do in general, but if you now look at associativity, then it just looks like this equation here, where whenever it's unambiguous, I leave out these blocks here. Faster and unit properties look like this. And analogically, co-associativity, I just get by reflecting pictures vertically. And now I also put the other one then. And at the moment, this is just notation. We do not do much with it, but maybe it's worth pointing out that we can think of this equality as allowing us to move one of the product along such a line and exchanging the different products. And also we could say, well, democratically, we could also define this as something like that, because they are the same morphism. And even though this is sensible, I will not use it. Let me also give another definition and then its graphical description. An algebra morphism between two algebra, say from A mu eta to A prime mu prime eta prime, is the same as a morphism of the underlying objects. Maybe I write explicitly now A dot to A prime dot, such that phi composed with mu is the same as mu prime composed with phi tensor phi, and phi composed with eta is the same as eta prime. And instead of writing such formulas, I could also do it graphically. This means that if I have my algebra A here, I first multiply and then I apply phi. Okay, with A prime is the same as taking phi twice. So here I have mu. And then here I would have mu prime into A prime. And this one, since this where I have eta here is the same as eta prime. And then analogously, you can define a co-algebra morphism between co-algebras by similar formulas, which when expressed in graphical terms are just given by vertically reflecting the pictures. If I take algebras as objects and algebra morphisms as morphisms, then I get a category. You can, it's a nice exercise to check. And it is a category. Right, it is a category. Define the composition via composition of the underlying map morphisms, and another exercise which where you maybe do is show that a circle S1 regarded as an object of the two-dimensional oriented cobordism category has a natural structure of an algebra and of a co-algebra. So this is an example of an algebra in a category which is not linear and not abelian. To do this, just recall what we said about generating morphisms of that category. Then we need another definition, which I will also do graphically. And then on Thursday, I will start with the result. Up to now, and also with the following, all the graphics is just to not to have to write equations. But the real relevance of the graphical calculus is for simplifying proofs or for producing proofs. I will give you one example where graphically the proof is very simple. And later on, we will see other examples also. So what we do here is remember the notion of a module or the bimodule over a ring or over an algebra in vector spaces. Analogously, you can do this in a monoidal category. We have an algebra, then we say left module. Over A, or we also just left A module. This is a pair, M row, where M, or maybe I should write M dot, is an object in C, and row is a morphism from A tensor M or M dot to M dot, such that, and I write this in formulas, but then directly will give graphical description. Row composed with identity on A tensor row is the same as row composed with mu tensor with the identity on M, or M dots to be precise, and a row composed with eta the tensor the identity on M is the identity on M. And to do this graphically, we say that row, this is a morphism from A tensor M to M that we denote as follows. Well, we could have some special symbol here, but very often I will also leave this out. And then this first property here says that if we say row is also, we call this also the action of A on M, or the representation morphism, acting with A once, it's here, and then acting another time is the same as first multiplying and then acting. And the other equality says that if I act after having the unit, then this is just the identity. In the same way, you can define a right module where you just have A on this side and then the graphical description. Will be like that. So you just reflect at a vertical line, and then the requirements are obtained from these by reflecting also. But this would be right module. And then an A prime bimodule is a triple M row, another row, such that M row is an A module, A left module, M, and the other morphism is an A right module. And in addition, they are compatible, and I don't write this as a formula, but just draw the picture. We have this equality. So here we have M and A prime. And we can also define a left co-module over a co-algebra. Just having an object, let's call it W, and then a morphism of this type, such that I get identities like these obtained from these by reflecting upside down. And finally, I can take, I have the notion of a module morphism. Say from F, from M row, I write it for left modules, analogous for right modules, so M prime row prime. So this is a morphism F on M and prime, or more precisely M dot to M prime dot, such that graphically we have the following. So we have a morphism F on M to M prime, And we get the same thing if we act with A. So here we have rho, and then apply F, or we first apply F and then act with A. So here we would have rho prime. And then taking the left modules as objects and morphisms of left modules as morphisms, we get again a category. And that's it for today. Okay. Do you have any further questions?
So if we define subalgebra algebra monomorphism, and if we want to find an intersection by the pullback of two algebra monomorphism, do we get to the question is the intersection of subalgebra or subalgebra? By the pullback of two algebra monomorphism.
At least under certain mild conditions on the category. But I haven't thought
We never saw
really about that. Maybe we should take this up separately. I cannot say much. Okay. So.